It's really great to be here. This was my very first Strata 4 years ago, and I haven't been back to New York since, so it's really exciting to be here. I'm going to be talking to you about how using open source tools, specifically for machine learning, can help everyone build better products, not just you, not just me, but everyone. So to give you a little bit of context on who I am, as Josh said, I'm with Qordoba. We are a Series A startup based in San Francisco. I'm the director of data science there. And as far as background goes, both of my degrees are in computer science. And my very favorite things are natural language processing, and that comes from when I was a teenager, I spent some time overseas. I wanted to learn another language. And so I did part of my computer science studies abroad while I was learning another language. So combining computer science and linguistics is something that I've always really enjoyed. And the reason I first came to Strata is because I got involved in distributed computing, because you can do better NLP if you have a lot more machines to do it on. So that's why I'm here. And I really love emoji. Part of doing NLP research involves trying to understand the data that you're looking at. And I feel like emoji can actually give you a lot more information than people give it credit for. So you see a lot of emoji in this presentation. So I've been working as an engineer for a little over a decade in lots of different areas. A lot of that has been computational linguistics. I'm pretty sure my friends think I'm trying to work on the universal translator from Star Trek, and while cool, that's not quite what I do. And we'll talk about that today. So to start off with, I'll give you a definition. I'll sort of lay down the baseline of what a good product is and what I mean by how to build a better product. What does that even mean? And I'll present that in the context of the platform that I've been working on, and that's in the field of localization, internationalization. And we'll talk about why that's so hard, what we can do to make it a little bit easier, and I'll give you some examples of why it's important. And then I'll dive into some of my favorite things, which is, of course, NLP and NLP's role in making internationalization easier. And then we'll talk about some concrete ways of how we're deploying our NLP models, how we're doing that in production alongside everything else in our platform, and what that continuous delivery process looks like. So the question that I always get asked, because the name isn't always very obvious, what is Qordoba? Well, we are a translation and localization management platform, and it layers on machine learning and smart process flows to enable companies to go international in a lot more efficient way. Our company mission is to see every product in every language by default. That's our vision. And we've reached a point with machine learning where it's possible to do international business in a scalable way. So we're taking this traditional industry and we're sort of modernizing it. And I would be remiss if I talked about the company without mentioning all of the people. These are some of the members of our team. We're very diverse. I really love that we have so many languages, so many native languages in the company. And we are also really proud of the fact that company-wide we're 38% female, and all of the people with circles around them, these are all females in leadership positions. So not just having females, but having them director level and above. That's, I feel like, a really big thing. That's part of why I really like working there. So let's start off by just defining what a good product is. What does it mean to build a better product? Well, it depends on your perspective. Your users, they have a very different idea of what a better product is, and what they think should be driving the engineering perspective and the business perspective. So what does a user care about? They want stability. They want to make sure that their data is always there. They want it to be reliable. They want it to be fast, always there and easy to use. And above all, does it solve my problem? So I want to focus on that as sort of underlying everything that we talk about. We're going to kind of go back to this slide because that should be what's driving all of our decisions, all of our motivations. So from an engineering perspective, we're concerned about scalability. We're concerned about how hard it is to maintain that code base, to write it in the first place, to add new features, to extend it, to fix bugs. We want to know that when we introduce new code, when we fix old bugs, new bugs don't crop up, those types of things. And above all, are we solving our user's problem? We're not just coding in a cave, we're actually writing something for someone to use. And from the business side, the business cares about having technology that can that can fuel expansion, not just in terms of the tech, but also in terms of like market growth. And if they want to go in a different direction, they want to know that their technology can scale with it. They want engagement from their customers. They want their customers to be happy. They want to make sure that they come back to their product, that it's sticky, all of these things. Lower costs so that they can keep the company running. But all of these things, underlying them, are the things that the user cares about, and that's, does it solve that user's problem? So that's just what we mean by better product. These are our goals that we're trying to achieve, and we want to really focus on what the user is looking for. So I told you we would talk about this in the context of internationalization. What exactly is that? If you haven't worked directly on an internationalization project, it can be kind of difficult to understand. It's a lot bigger than just having translations for things. But this is a pretty simple example. This is an Airbnb ad for my apartment. So I mentioned I was in San Francisco, I'm in the Mission, rent is outrageous, and there are a couple of reasons why I might want to put my apartment up. Number one, to pay the bills. Goes without saying. I also mentioned that I learned another language when I was a teenager, and that language was German. So what I would really like is for Germans to come and stay with me, because that means that I can keep my language skills up to date. That means I can keep up with current events and things that are going on over there. So I have all these motivations for wanting to do this, but I don't necessarily have visibility into what the German version of my ad looks like, because it's something that just sort of happens automatically on the Airbnb side. So if I really want to target Germans and I want them to come visit me, I'm probably not going to be very successful with an automated translation of this ad. So if you look at the word mörderisch, it means the same thing in German as it does in English. Diese Wohnung befindet sich an einem mörderischen Standort. It sounds like a dangerous place instead of a really good place. So that's just one really simple example of why internationalization, why it can be hard, and why it can really sort of backfire in terms of achieving your goals and trying to make your users happier. So I kind of talked to you about our vision for what we think internationalization should be like in the future, but let's talk about what it looked like in the past. It's a really complex process. It involves a lot of humans, a lot of things, a lot of manual processes. And we've all seen the results of that in the past. Does anyone remember this campaign from the 90s? It was wildly successful in the US. And when they expanded that to a Spanish-speaking market, it was a little less successful because their translation of that was something more akin to, "Are you lactating?" which you can imagine did not help them sell much more milk. I want you to think about, so if you're not familiar with Nicole Miller, it's a fashion home furnishings company, and I want you to think about how you might localize an ad like this. It's pretty effective in English, but it has a lot of cultural references to it. So if you were going to translate that into German, it's okay if you don't speak German. It's roughly akin to, I realize that when this telephone service flashes, it can only mean one thing, and that is so much less effective. So it's not just about finding the right translations, it's really trying to capture the essence of what you're trying to communicate and still make it effective and really still hit those goals. So we think that there's a better way. We think that we could really just make it more efficient and more localized than it's ever been before. So really underlying that concept, you can think about it as being the Docker of content, and it's really just pulling out that content into its own separate location and having a central location for organizing everything inside of that content layer. Because you want to be able to, that allows you to coordinate activities between all of those different teams that we saw, and isolating content into its own layer. It improves the quality and reduces cost because all of a sudden you can eliminate a lot of the manual repetition, and you can add machine learning to the mix. And it's not just about separating things by English and Spanish and German by language. It's also about by domain. So if you're writing obituaries, you don't really want to have language that would be appropriate maybe on social media. So it's really about having containers inside those containers, and like the platform is built on top of Docker, on top of Kubernetes. The platform itself is in containers. You're probably running an application that also runs containers. It's really just containers all the way down. It's not limited to just per language. So in terms of localization, some of the things that we're solving by adding machine learning, Normally in applications, if you haven't localized, your content is really disorganized and it can be deeply embedded. So by putting it into its own layer, it's completely separate from your application logic. And you get a lot of things being translated over and over again. Well, we solve that by just having a translation memory. And anytime we see a string that we've seen before, we give it the correct translation. And if you have a translation that's wrong and you don't want to have to touch that in lots of different places, you just correct it once, and then the changes get reflected everywhere because you're using this translation memory concept. And adding anything new can take time, but because we're using machine learning, we can have automatic translations that are a lot closer to correct, if not correct, rather than having to have a human look at every single string every single time. And that also enables us, because it's in a separate layer, we can have everything in context. So instead of a linguist receiving a spreadsheet of just text without seeing that hotline bling refers to these cell phone covers, they can actually see it in context and they can make a translation in its original format. So you'll get better quality. And then it's also a lot faster from a deployment perspective because we have this GitHub integration that essentially means anything that a user does will automatically get pushed in as a PR, and you can set that up as part of your continuous delivery process. So one last example for localization. So these are 3 neighborhoods within San Francisco. This is a picture of Dolores Park. That's where I live. That's my neighborhood. There's also Chinatown and Japantown, different areas within the city that have very distinct cultural identities. And let's say I'm a produce vendor and I'm looking to sell, let's say, watermelon. I come up with this fantastic ad that I want to deploy citywide. That would be a lot more effective if I had maybe a Spanish version in the mission, a Chinese version in Chinatown, and a Japanese version in Japantown. And it's not just about text, it's also about images and video and audio files. It's a lot more than just content. So this is just an example of how I might be able to advertise a bit more effectively by localizing. Okay, so now we get to the NLP side of things. One of the first projects I worked on when I was hired is looking at the emotion associated with a piece of text. And that's important because sometimes if we just change one word in a sentence, we can come up with a completely different meaning. And so by understanding the emotion that that text evokes, we can get a good sense of whether that's a good translation, a bad translation, or just a little bit off. So a couple of examples of that. These are sentences that we put through our affect detector. This first sentence, I had dinner with my wife, you can imagine had a very specific reaction. The one that we got from our machine learning model trained on a specific corpus was that of fear, which says something about the corpus that it was trained on, is all I'll say. And if we just change one word, changed it from wife to girlfriend without even changing the gender, we got a very different reaction. So if you look at that from the translation perspective, we're a produce vendor, we're advertising the mission. I may want a Spanish version of that. My English version may seem fine, like I'm sad, I need some help. But then if I have this translation that I think is correct, it might actually not be. It might be something more akin to get off your lazy ass and find a job, and you wouldn't find many workers in the mission, I imagine. And back to our original example, those 2 sentences would evoke very different emotions. And so that can give us an idea of how accurate our translation is, and it can help us automate things because the whole point is to make localization easier and faster by automating and using machine learning. So what we set out to build is this affect detector. And so the basic architecture of the platform, it's a standard microservices architecture. And so affect detection is really just another microservice. So we have our front end, which is what our user sees. We have an orchestration layer that sort of ties together all of the different microservices. And then affect detection was just one more of those. So we needed it to be available as a REST interface. We needed something listening and able to respond and generate predictions. And then we also just needed it to be able to scale in the same way that any other part of the platform would need to scale. We need to be able to generate as many models as we need and do that in a way that's cost efficient and that sort of fits in with the rest of the platform. And we also really cared that it was open source. That's something that's always been important to us as a company. We've chosen to use a lot of open source tools. And in this case, what we decided to use is Prediction.io. And that's based on, so part of that is also Apache Spark. Prediction.io is an Apache incubator project. And if you're not familiar with it, you might be familiar with this scene from Apollo 13 whenever they lock a bunch of the rocket scientists in a room and they dump out a bunch of components and they say, okay, we got a man, he's gonna die unless we find some sort of solution with just these parts. So it kind of feels like that because there are a lot of different pieces, but it's almost all of it's open source, and it's really allowed us to achieve those goals that we set out to accomplish with all the whole better product thing. So before I go too far into the details of how we're using those open source tools, I want to kind of take a step back and just give you a really quick overview of NLP if you're not familiar with it. Because machine learning does look very different from from the rest of the application, from anything else you would traditionally create. And so I want to talk about why it's different and sort of the theory behind it and why it has to be different, why it's fundamentally has different resource requirements. So this is going to be very brief and very simplified, but essentially what you're doing when you're processing human-created text, language-related data, is you're taking something that's text-based, and the feature extraction phase just refers to turning that from language, from text, into some sort of numerical format. And this is the piece, depending on what you do within that feature extraction, this is what makes it language independent. This is how we can have one set of code, and it can be applicable to all of the languages. That's what we use. We have literally one image, and then we send in every different language through it. We build different models for each of them without really changing anything except for parameters. So once you've extracted features, and those features just are a way of representing your text in a way that you can do math on it, in a way that you can plug it into a formula, that's where you do training. And by training, you're essentially giving it an answer key. You're telling your model, this type of vector means this certain thing. So the label of 1 is arbitrary. It could be a label of A, B, C. It could be fear. It could be joy. It could be anything. It's really just a classification approach. So training is where you take all of these vectors of data and all these different labels, and you essentially fit coefficients to an algorithm that allows you to, when you see a new piece of text come in, derive what that label should be, what that classification should be. And that's the prediction phase, where you send it a new piece of text and it plugs it in to an algorithm, to a formula, and it spits back out an answer, a label. And that's all well and good, but if you don't know how accurate your models are, then you're not really going to know how useful they are. So the cross-validation phase is where you go through multiple rounds of training, and training itself is already resource intensive. But in cross-validation, you take sort of random subsets of your entire training set, and you score those. So you train a model, you score it, you train another model, you score it, you train another model, and you do that tenfold is standard. So another very resource-intensive step. And then based on the results that you see, you might change some of the parameters that you're inputting. So hyperparameter tuning refers to adjusting some of the, kind of tweaking some knobs and dials without necessarily changing any code, but just giving it different parameters for generating that formula. So that's kind of it. That's the basics of it. Some really quick examples that, a little bit more detail about the feature extraction phase. We might take that content and tokenize it, so split it out into words or into individual pieces. We might use unigrams and bigrams, and then really just count up how often they occur. And that's how we would come up with a vector. So it incorporates features of the text, and it's really just a way of transforming that into a numerical format. And then for training, we can really just run that through one of Spark's logistic regression implementations. It's as simple as that. It expects the training data in a certain format, but otherwise it's pretty straightforward, and it will give us this binary blob at the end that we can then use to generate predictions. So for the prediction phase, we have this new piece of text, and we run it through that exact same featurization pipeline that we used during the training phase. And we send it to that binary blob that Spark spit out, and it will give us a classification. And that's what we send back to our user. Cross-validation, as we talked about. Tenfold is pretty standard. You go through training over and over again, and you just score things. So you look at the labels and whether those labels were close to what you were expecting. and your results, usually an F-score is what people look at. So that's more of the theory of what we're using. So what are we doing more concretely to build this better product? What are we doing within our platform to result in something that's useful to our users? So I want to go back to the goals that we had, specifically from an engineering perspective, because we're going to be talking about how we're implementing those steps. We care about speed, we care about stability, all of the things that you generally think about when you talk about continuous delivery. You're measuring certain things along the way, and you're trying to automate it so that there's less human involvement and less room for error. Well, this is a view of some of the tools that we've chosen to do that. And I don't want to go too deep into that just yet. I want to talk about some of the problems that we've encountered while implementing some of those machine learning approaches, some of those NLP techniques. And a big one, probably the biggest one, is just that this is a whole platform. It's a lot of it is based on Scala's Play framework, and so it's just these services that sit around listening, and they have a very different footprint from a lot of the training and cross-validation that we talked about. And so putting all of those together into one environment so that they can talk to each other and sort of run alongside each other, the way we solved that problem was to just put everything just to containerize it and put it into a single environment, and then just have it specify how many resources it needed when it runs. So training can say, I'm going to need 16 gigs of RAM and 3 CPU cores, whereas everything else is going to request a lot less. And what that looks like, so concretely for us, before I joined the team, when we didn't have affect detection and it was mostly just the application running, everything was in this nice happy Mesos cluster. We're a Scala shop, so everything was packaged neatly into a jar and then just sort of uploaded and made available. And then the circus came to town and we had to change things. So what we started out by doing is just putting the affect detection into a Kubernetes cluster. And that worked out so well that we then added the rest of the application into it. So we just had all these different containers running, requesting different types of resources, but really on the same hardware. And that just made it a lot easier to maintain instead of these two separate, like Mesos and Kubernetes. It was really hard from an ops perspective. So putting it all together really simplified things. The other problem that we ran into before when we were managing the VMs ourselves instead of running it in Kubernetes, is that those IP addresses were not necessarily static. And what we really like about Kubernetes is that it literally looks like this. What you see in pink, that's how we call a service. We don't care at all which node it's running on. We just know that we want the automation service or the reporting service. And we don't have any port collisions. We don't have to care about which node it's running on and whether there's already a port 80 being used. Kubernetes solves all of that for us, and it means that we have a lot less configuration to deal with. Because configuration is a total pain. And what we saw is that our configuration was scattered all over the place. It was buried deep. It was hidden in all these nooks and crannies. It was a total pain. But what you see in Kubernetes is that there's these special things called config maps. You create them once, and then you can reference them from any service. And it was really a way for us to organize and corral all of our environment-specific stuff and put it into one place. And the cool thing about that is that it's all stored in GitHub. That means that we can have scripts like this. If our entire cluster goes down and we need to build it from scratch, this is a portion of our create cluster script. So all it does is it checks out a branch, and then it goes in and it creates these config map objects from just whatever's in our repo. And so we were able to standardize that across all of our microservices and basically write a script that just loops through, okay, whether I have 10 services or 100, I can create the objects in the same way, and it's a lot easier to maintain. In your configuration, if you need to move into a different environment, stand up a new cluster for your marketing team or for someone else, it's super easy because you just, you clone the branch and then you change a few things and then you can run these scripts. The other problem is that machines die a lot. And again, being able to reload your configuration from GitHub, I can't overemphasize how awesome that is. It makes it really easy to recover from machine failures. And probably one of my favorite changes is, so you're probably all familiar with this. Releases are really time-consuming. It's really frustrating. Even sometimes really well-established CD processes can still have some manual pieces in them. But we've come up with a solution that we're really happy with, and we ended up migrating. Essentially, we've been in production with this for a while now, and things are so much smoother. We trigger deployments just by PR merge, and this means that as a developer, if I write code, all I have to do is merge it into a standard branch, like develop or master, and it's an image automatically gets built, and it's pushed out into Kubernetes, and I don't really have to think about it. All I'm concentrating on is my code, and that means that your ops team isn't burdened by a lot of this. A lot of it is just really automatic. And this Kubernetes object that's called a deployment, that handles a lot of the specifics for you. So even just within Kubernetes itself, it takes a lot of the work from your plate. So what that looks like is we use a couple tools to accomplish that. And you can generally draw a line between the top is your persistent layer and the bottom is more your ephemeral. Those are the things that are running your application and actually physically doing the work. And so you have your application code in GitHub, and you just give it a Jenkins file. You tell it how it's supposed to build itself, how it builds binaries, how it builds an image. And Jenkins will pick that up. Like, you pretty much just have to point it at the repo when you create this thing called a multi-branch pipeline job. You put it at the repo, and then it will automatically build this Docker image for you and send it to your container repository. And that means that you have these images with your application ready to go, sitting there anytime you need them. You don't have to rebuild them. If you have new code, you can, but they're always ready to go. And then we have this other tool called Weaveworks. I don't know if anyone has tried it before, but it's so neat. They have this cloud product that we use, and essentially it will just watch your container repository. So anytime a new image shows up, it will go and deploy it. It'll not only push it to Kubernetes, but it'll also save the changes in GitHub. So this is where all that configuration that I talked about is. It's a separate repository. It's not part of the application, but it contains all of the environment-specific stuff, and it tells you which version of your image you're running in any given cluster at any given time. And Weave manages all of that. So it picks up new changes from your container registry, commits them into the repo, and deploys them into your cluster. And so you, as an engineer, all you're doing is merging your changes into the develop branch, and everything else sort of picks it up, and you don't have to think about it. And you can be moving on to make other fixes, to make other changes, and then once this process is complete, you go back 2 minutes later and you check it, and it's a much faster iteration process from an engineering perspective. The other really cool thing about this setup is just that adding capacity, sometimes that can be non-trivial depending on the type of cluster you're running. I mean, with Mesos, it was not as straightforward as we would have liked, but with Kubernetes, because we use the Google Cloud hosted solution, it's like they manage the Kubernetes cluster for you. You have to think about pretty much nothing. You go and you click on this little pencil icon and you change this number, and that's it, and your cluster gets bigger. And so what you're concentrating on is writing your application code, building your images, and then the infrastructure takes care of everything for you. It's a dream for both operations and for engineering and data science. So to go into a little bit more detail about what that affect detection container looks like, because it might not be all that obvious. We talked about all those steps involved in deploying a prediction model. You have to load in your data, you have to build your binary objects, you need to train things, and then you can deploy this prediction that sits there and waits for input. And if you were just to write that all into a single image, you could do that, but again, that would be pretty inefficient because all of those things have different resource requirements, and it really wouldn't make much sense. But you do need the same code base, and so the way we approach that is to use the same image but give it different entry points. So we don't, all of our data, none of that is stored within the image, that's stored somewhere else, but we can basically trigger a data load by just giving it the data load entry point. We can trigger training by just referencing the training entry point. And so we're still using the same code base. We're still using the same engine definition, the same model definition, and the same data on the backside. But we're able to generate all of these different containers and run as many as we need, as many times as we want to. If we get a lot of predictions coming in, we can just spin up more prediction containers and run training as normal in the background as needed. And that also means that instead of just using logistic regression, we can add other types of algorithms. We could use things other than Spark. We could really expand out and using the same machine image under the covers. Again, this supports every different language. It's the same code base, but it really scales out very nicely. And what does that one single image look like? It's pretty basic. It's also pretty big, but it's stock Ubuntu with Java 8. We build Spark ourselves from source because we want these native blasts. We want the vector math optimizations. And then we're using Prediction.io. I don't know if there's been an official release for this, but there is a release candidate that we're already using because we needed some of the new features. That's the advantage of using open source. You can go in and pick the latest version of Spark, the latest version of whatever machine learning libraries you need. So pretty simple. And we have a router. This is what determines when it receives a new piece of text, which language is this, where do I send it, which container does it go to. We use a builder container for that. And what that is that's a sort of application-wide base image. That means that everything is running on the same version of the JVM, the same version of SBT. We used to use Docker and Docker for that. But, and the reason we did that is because those build images can get really big. And for our runtime images, we really only need a JRE and the binaries that we've just generated. So we would use Docker and Docker to come up with these much smaller runtime images. But we started using multi-stage builds. That's something Docker released, I think, around April of this year. They are amazing. I highly recommend them. Because these build images can get really, really large. I think even just Ubuntu alone is several hundred megs. So having a really thin and light runtime images has made a major change for us. It's brought our image sizes down from like a gig to 100, 150 megs. It's a big difference. Okay, so those are some of the sort of concrete things that we've done, but let's go back to this. The whole reason we've done that is because we were trying to build a better product. And what does better mean to you? What does that mean to your users? What does that mean to your business? That's different depending on the application that you're working on. But always keep in mind what a user cares about and translate that into that should be driving what engineering cares about, what data science cares about, what the business cares about. But I'll leave you with, the last thing I want to leave you with is just a challenge. We talked about a lot of things that we've done, a lot of problems we've solved, and a lot of ways to make our product better. But one of those ways is really just to not build products that scale, but to build products that scale in terms of content. Because that's really one way of making everyone's product better. It's not just about our product itself being better or us giving a better product to our users so that they can build better products. It's also about sharing these things with our peers, everyone in this room. It's also about writing open source code and being able to see what other people are doing. So by sort of containerizing your content, putting that into a separate layer and treating that differently, that's a way that everyone can benefit from you building a product that's better for you, for your users. It really benefits everyone. So I think I'm about out of time. If anyone has any questions, I'm more than happy to stick around and answer them. But I think we're recording, so is there a microphone that's being passed around? Okay.
If you have a question for Michelle, just shout it out, and Michelle just repeat the question.
Yes, sir?
How long did it take to implement?
How long did it take to implement? Oh, how many people? The whole platform or just the affect detector? The question is how long it took to implement the whole thing, and by that, do you mean the entire platform or just the affect detector? Well, the company's been around for 3 years now, I believe, and we have 12, 15 engineers, something like that. Go ahead.
How do you, obviously, for people who are developing models, these things come live very, very quickly.
Sorry, I'm having trouble hearing you.
Are you doing continuous delivery or continuous deployment?
So we refer to it as continuous delivery because it encompasses integration and deployment. I would say it's a combination.
Okay. So you have systems that go live very quickly, right? As a result of changes that people are committing to the repository in a certain whatever branch they're committing to. And so how do you do regression testing and just making sure that when somebody makes a change to a model or some code that affects your linguistics that your previous use cases continue to work?
Yeah, that's a great question. He's asking how we maintain quality because if we're automatically deploying changes that someone commits into a branch, how do we make sure that previous models are still working, that major things aren't breaking? What type of regression testing do we do? We have automated tests is number one. We run it in different environments. We have a dev environment testing, like a staging, and then a production. And we're pretty good about having at least some sort of human look at things in some sort of environment before it goes into production. But the other thing that we really like, Weave has this really nice UI that if something has gone out and you want to revert, it's like a one-button click. And because things are sitting in that container registry, we have everything's versioned and we can very easily go back to that. And Kubernetes manages that rollback very gracefully. It's all kind of built into the platform. So there's a lot of stuff that we don't have to do ourselves. And I mean, when we identify something, it's pretty fast to roll back, but we do try and have good test coverage so that we don't have to do that.
Right. I guess, my take is that, whenever you make a change to a model, you have to continue to make sure that, every previous set of use cases works, right? Again, so your entire training set, you want to rerun against your models. Is that not true? Right? So, if you do that, presumably you've got, an exponential growth as frequently as you change the models for your system that goes live. So does not each testing cycle increase in length of time and scope and activity?
Well, and so the question is, so every time we build a model, are we testing old functionality on the original data set?
Your entire training set against your new models, your code changes as a part of deployment.
As a part of deployment. I wouldn't say that we go to those extents. The term GitOps, and I forgot to credit Alexis Richardson. He coined that term. Every change that we make is sitting in GitHub, so we have a record of all of that. And whenever we build new models, we don't necessarily use the entire training set. So a lot of those parameters that we change might be taking out different parts of our training data, so we don't necessarily have to rebuild on the full training set. And it also depends on, remember that we're building these languages per model, so it's not like we have billions of sentence pairs per language. It's a much smaller order of magnitude. Our English one is the largest one, but the other ones, they're not huge. So it's not that much different, and because we can scale it out so easily and just request more resources if we need to, we really haven't gotten to a point where we just can't handle it. Anyone else?